Hi, I'm Tudor Davies at Spectrum Signal Processing. We would like to show you the XMC 1151 with the repetitive capture example, which is an example that can be used for LIDAR and radar. So what we're going to show you is, first of all, we've got the XMC 1151 mounted inside this PC. We'll get you a close-up shot on that. The XMC 1151 is here mounted on the card, the carrier card. This is a Linux PC running a Red Hat Enterprise Linux 6.5. Over here we've got some test equipment connected to the XMC card. First of all, we have an external sample clock. External sample clock is at 1 gigasample per second, 1 gigahertz clock. So that's going from this signal generator into the clock input on the XMC 1151. Second, we have the signal. The signal is coming from this signal generator in the middle. This one has a 200 megahertz signal at which we're AM modulating at 50%. And right now we're setting it with a modulation frequency of 5.1 kilohertz. And third, we have this signal generator, which is giving us a 5 kilohertz square wave, which we're using as the trigger. So this represents the LIDAR trigger. That is going into the input that's currently labeled as 1 PPS. It's actually just a general purpose I/O, GPIO. So that's being used to trigger each capture. So on each event of the trigger, we will capture a burst of 4K samples, 4096 samples. That's a user adjustable amount of time. So the trigger occurs, we wait for 80 clock periods at 1/8 of the sample rate, and then we will capture 4K samples. Both those are user adjustable, and then we will save those samples to the memory on the PC. First, we save it to the memory on the FPGA, then we DMA it to the PC. We will take 256 of those 4K captures, 4K sample captures, transfer those to the PC memory. And then what we do is we take that data on the PC, we'll capture it and plot it in MATLAB so you can actually see the samples in a whole 4K, actually a whole block of 256 of those 4K samples. Okay, so we're also displaying here on the scope. We've got the yellow is the trigger, so that's 5 kilohertz, and we've got, this is the 200 megahertz AM modulated waveform. You can't really quite see the blue very well on this scope. If we had a better scope, we might be able to see the actual AM modulation. So let's do a capture, and we'll display what you see in MATLAB. Okay, so this is the XMC 1151 mounted on this PCI Express carrier card. So you can't actually see the 1151 card itself from here. This is the carrier card. It's got this fan which blows air down over the XMC 1151 to give it a little bit better cooling. And then on this side you can see the cables which actually connect into the back of the PC. This would be on the front panel if it was a VPX card or CPCI serial. So one of these is the signal coming from the signal generator, one of these is the external sample clock, and one of these is the trigger, and that's going into a GPIO, a coaxial GPIO on the panel. Okay, so what we're going to do, we've got all the signals coming into the board, so I'm just going to run this example software which we call XMC 1151 repetitive triggered snapshot. So that's taking a snapshot which is about 4K samples long, and it's going to do that at a predetermined delay after the trigger. So I'm just going to run this example, and it scrolls through some text that tells me that it's done. Next thing, I'm going to just cheat a little bit. I'm going to use the commands that are in history. The next thing I'm going to do is run this command which actually loads the data which we've saved to a file, and we're going to load that into MATLAB. And then finally, we're going to plot that data And here you can see that you can see the AM envelope here. Now if I actually set the signal generator AM modulation to be exactly the same as the pulse repetition frequency, I'm always going to see the same level. So I've actually set this to 5.1 kilohertz, so it's advancing in phase a little bit on each capture. So I'll zoom in here, blow it up, and I'll pick the little plus arrow and I zoom in. It actually looks quite smooth in this case. Now this is sort of cheating because what I'm actually getting is this is one capture, this is the next capture, but I'm just capturing a little bit later in the actual AM envelope. So I'm going to change the frequency of the AM modulation a little bit. So on the signal generator, I change the AM modulation frequency, and I'm going to make it just a little bit below the sample rate, 4.9 kilohertz, or below the pulse repetition frequency. And I'm going to do another capture. Run the example again, saves it to a file. Load the file. I'm just using the same file name over and over again. And then plot. Now here you can see it looks a little bit different. I'll blow it up. And you can actually see the little jaggies, which are each successive capture. So in this case, our AM modulation frequency is a little bit lower. So instead of having the rising signal on here, we're getting the falling part of the signal. So you can see this from there to there. That's one capture, and then the next cycle, after at the 5 kilohertz trigger rate, I'm actually starting a little bit earlier in the AM modulations envelope. So I'm actually catching a little bit earlier and earlier and earlier, so I can actually see the jaggy. So from there to there is one capture. One capture is 4K samples. So if I zoom out again, I can see that the envelope is nice and smooth. So what that tells me is we're not losing any bursts, any captures. If I suddenly saw a jump that was going the wrong way, I would expect that I have actually lost data. So that's one of the easy ways that we can tell that we're not losing data. So we can play around with this a little bit. If I change the sample or the AM modulation, let's just see what happens if I go to 1 kilohertz. And then I'll make this window, I'll hide this window, save it. I'll do another capture. You know what, I'm going to make it 1.1, so it's not exactly a subharmonic of the trigger rate. Got that. Okay, now we've gone to a lower sample rate, or lower capture rate. So now you can see different sections of the waveform. I zoom out a little bit. You can see that it's fairly consistent. So one thing that we see is that each one of these captures is one 4K sample period. And there you have it.